Hey guys, what's going on? We're going to do the couple of these homework problems. I know a lot of y'all were struggling with these today, and we did number 1 in class, so hopefully that made sense. And after talking about number 1 more, I think I have a even better way of explaining it now. So if you're still kind of struggling with number 1, come see me at some point. We'll talk about it. But I'm going to do number 2 and number 4 today from the homework. So let's just dive right in here and get started. We have number 2. We have a ball, and it's dropped from rest at the top of an 800-meter tall building. The ball freely falls with constant acceleration for 8 seconds. At this time, the ball reaches terminal velocity. All right, so a couple things. First of all, what does this term mean, terminal velocity? All right. You drop an object off of a building, for example, that object will begin to accelerate towards Earth at about 10 meters per second squared. That's the acceleration due to gravity. All right, and it's going to speed up and speed up and speed up and speed up. Now, in AP Physics 1, we don't really deal with air resistance most of the time, but air resistance is a thing. And when the force, we've got an object that's falling, being pulled down by the force of gravity, and also has an upward force, a force of air resistance. Right? Now, as the ball falls, air resistance is small when the speed is low, but as the speed gets bigger and bigger, increases speed, the air resistance force becomes larger and larger until at some point the air resistance force actually is equal to the downward gravitational force. When this happens, the object no longer accelerates. It still goes down, right? It still has downward velocity, but it stops accelerating downwards and just goes at a constant speed. And that speed is called terminal velocity. All right, so that's what that term means. And I know that some of y'all didn't know that. That's totally fine because I did not tell you about that term. So now we have. So, all right. So basically, what terminal velocity is? It's the speed at which we stop accelerating. All right. So part A wants to know how far has the ball fallen when it reaches terminal velocity. So let's draw a little picture here. Pictures are great for these problems. Here's my little dude. He's a giant apparently, and for a little longer. All right. So there's the ground. So now you have two options here, guys. You can call when you guys are doing problems like this, you get to pick what the positions are, right? It's all relative. If I wanted to, I could call like this spot up here, I could call that my 0, and I could call way down here like negative, I don't know, 2,000 meters, and this could be where the guy is, that could be negative 1,200 meters. If I really wanted to do that, I could do that. That would be ridiculous. I don't know why I would do that, but I could do that. I'm not going to do that. That's silly, but you get my point. You guys, it's all up to y'all about when it comes to what position is what. Now, most of the time, there's two primary options. One is, hey, make the ground my 0. Call this 0 as x equals 0. Remember, x is position. And then call where I'm going to start this thing, call that x0, and call that however high up you are. In this case, I'm 800 meters off the ground, 800 meter tall building, so call that 800. The other option is to call this 0 and call this negative 800 because 800 meters below, right, down from that point. I don't like that as much. I like to keep the ground as my 0 point, but you could do it either way. It won't make a difference in the answer. You get the same answer regardless, but you do have that option. All right, so okay. Anyway. Yeah, so I'm going to call this 800. That's my initial position. Now, remember the guess method, right? We're going to write down everything we know. My initial position is 800. The time I'm talking about here, the ball freely falls with constant acceleration for 8 seconds. My time is 8. T is 8. I'm at the top 800-meter tall building, and I know acceleration due to gravity is negative 10. That's my A. Negative, that does matter, meters per second squared, 8 seconds, 800 meters. There we go. And what am I looking for? How far has the ball fallen? All right, so I want to find my final position. Where will the ball be after these 8 seconds? All right, so there we go. So that's my equation, or that's my givens and my unknown. I'm going to pick an equation. Let's see, I got, my initial velocity, also know initial velocity, don't I? Initial velocity is 0 because it says it's dropped from rest, and that means I'm not moving. All right. So I know all this stuff, so I want to pick an appropriate equation. It's going to be x equals 1/2 at squared plus b0t plus x0. All right, then I'm going to plug and chug, substitute and solve. So x will be equal to 1/2. A is -10. T is 8. Square that, don't forget. V0 is 0. T is 8 again. Plus x0, which was 800 meters. All right, so this just goes away, right? Because 0 times 8 is 0. 8 squared is 64. Times 10 is 640. Half that is 320. But it's a negative. Don't remember, negative 320 plus 800. That's going to be 480. Now, this is not the answer to the problem, right? This is the position I am in. So my initial position was here at x0 at 800. My final position is 480 meters. Right, that's where my final position is. So how do you find the answer? Well, we want to know how far it's fallen. That's displacement, right? That's how far we've fallen. Displacement, don't forget, is a change in position. Well, there's my initial and final position. So how do I find displacement? Final minus initial. So 480 minus 800. And I'm going to get negative 320. And that's how many meters I have fallen. Why is it negative? Because it's a vector. What direction did I go? Down. So it makes sense that it's negative, right? I went down towards the earth. You could, you could have called down positive, I suppose, but that'd be weird. So down is usually negative. So that's why that's the answer. All right. Let's go to part B. What is the terminal velocity of the ball? All right. What am I looking for? What are my givens? Again, I know my initial velocity was 0. I'm accelerating at a rate of negative 10 meters per second squared. Oh, come on. Weird. And then also I want to find my final velocity. Oh, in 8 seconds, right? Because I'm falling. Oops, sorry, I read an F there. I don't know why I wrote an F there. It's weird. I meant to write a question mark. And then I know my time is 8 seconds because it says what is the terminal velocity of the ball. So at 8 seconds, I've reached my terminal velocity. What is it? It took 8 seconds, right? These are the I don't care about position here at all. I don't really care how far I fell. It's not part of the problem. So I'm going to find an appropriate equation, and that equation is going to be V equals AT plus V0. I don't need position here at all. This equation came from our derivation from Friday. So my final velocity will equal negative 10 times 8 plus 0. My final velocity will be negative 80 meters per second. Why negative? Because what direction am I going? Going down. All right. And then part C, what is the total time that the ball takes to reach the ground? All right. Well, we already know from part A that it took 8 seconds, right, to go to this position. Okay. So I got to go that much more. I still need to go 480 more meters, right? I fell 320 meters in 8 seconds. So I still have 480 more meters to go. So how long will it take to fall that far? At constant speed, right? Because now I'm at terminal velocity. I'm not speeding up anymore. I'm going at constant velocity. That's nice because that makes our equation really easy. With constant velocity, we can use this equation. Right? You can use that equation. Now what's my givens? Well, I know my velocity is negative 80. I know my initial position. My initial position here is the final position from part A, right? Because that's where I've already solved part A. I don't need to solve it again. I know where I am in part A after those 8 seconds. So that's my initial position here. That's 480. My final position is 0, the ground, and I'm looking for time, t. Plug and chug. Plug in the numbers, do the math. All right, so x is 0, v is negative 80, t is t, plus 480 here. I'm going to subtract 480 over here, negative 480 equals negative 80t divided by negative 80. Both sides, these cancel. T will equal 6 seconds. That is not your answer, though, right? Don't forget, you took 8 seconds on this side over here to fall to that point, and then 6 more seconds to reach the ground, right? So you got to add them up. So 6 plus 8, 14 seconds. That is your answer. All right, cool. Let's go to the next slide. Alright, let me get my pen on here. Okay, so this part D, draw a graph of the ball's velocity as a function of time. I'm not looking for a quantitative graph. Qualitative is totally fine. Qualitative means just the shape, right? And I'm not too worried about the numbers lining up perfectly, but just get the shape right. On your quiz on Wednesday, I will be asking you to make a quantitatively accurate graph, so be ready for that. But in this case, I'm speeding now, and also I want to make a note here. These really should be negative numbers, because I am going in the negative direction. Just forgot about that when I printed this off, but minor detail, but a detail nonetheless. So we are speeding up. We have an acceleration of -10 for 8 seconds, and then we stop. So I'm going to go find 8 seconds. That's right here, and go up to about -80. I'm going to draw a straight line, straightish, down to the origin there. And then once I reach that terminal velocity, I stop accelerating. I just go to constant speed. So it's just flat. All right, so I'm accelerating, speeding up as gravity pulls me down, speeding up, speeding up, speeding up. But then right here, I reach terminal velocity. I no longer accelerate. I go at a constant velocity, so it's flat. So your graph should look something like that. For position, I start at 800 meters, right? I start here, and I know I'm going to end up at 14 seconds. I'm going to hit the ground right there, right? So I got to connect those 2 points, but I should be curved for 8 seconds because my velocity initially is low, and then it's going to gain speed over time, right? So it's going to start off low and gain. Should be curved, 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 curved until here, and then it just goes straight at a straight line. I'm not drawing this very well, but you get the idea. So it should be all in here for 8 seconds. 5, 6. Whoa, what happened? Why did I do that? Why did I do that? That's weird. Redo. Oh, bizarre. Alright, let me draw it again. Oh, why did I take away my drawing? I don't know. So, what was I saying? Right, so curve. Oh, you start here. We curve it. Curve, 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 curve. Until about here, and then it's a straight line down. This is a terrible drawing, but you get the idea. So this region in here for 8 seconds. 5, 6, 7, 8, yeah. A region in there, it should be curved because it's accelerating, right? It's speeding up. It's getting more steep, right? As the graph, or as the object falls. But then once it reaches this point here, ish, somewhere in that region, we stop accelerating and we go at constant velocity. So it's a straight line, right? Constant speed. Okay. Number 4. All right, number 4 is about a rocket ship, or a rocket taking off. It says it fires from rest. All right, so all my variables over here. All right, from rest, I know that means initial velocity is 0. Acceleration is a positive 6, going up, right? Meter a second squared, meter per second, what units in there? And then t is 11 seconds, at least it is for now. After this time, the engine shuts off, and the rocket freely falls back to the surface of the Earth. Draw a graph of the velocity of the rocket as a function of time from t equals 0 to the time the rocket strikes the ground. All right, actually, interesting. You can't actually draw a graph because I made the numbers too big. You can't do it to where the rocket strikes the ground, but you can do it until the rocket stops moving upward. So let's see what the graph would look like. Let me insert a line here, as I can't draw straight lines. Let me insert a line. There we go. So if this is a velocity time graph, right? It says the acceleration is 6 for 11 seconds. It's a velocity time graph. The slope is acceleration, so that means that my slope should be 6 for 11 seconds. So after 11 seconds, what should my velocity be? Well, just 6 times 11, so 66. So I'm going to write in it's 11 seconds, my velocity should be 66. So right about here, I'm going to draw a line down to here. Something like that. That's what it should look like. Let's make that thicker so you can see it. Okay. There we go. So that's the first 11 seconds. And what happens after that? Well, then it falls, the rocket shut off, and the rocket falls freely back to Earth. Once the rocket shut off, the only force acting on the rocket is gravity. The acceleration of gravity is 10 down. It's negative 10. So now I'm going to go at a slope of 10 from here down, something like, should look like about like that, more or less. Okay, so something like that. So that's your graph should look something like that. Now, this is now, please keep in mind, this is not when the rocket strikes the ground, but it is as much as we can do with the space provided. And I'll talk more about the rest of this in a second, like right now. All right, so that's what our graph should look like. Let's go to part B and start doing some calculations. Okay. Determine the height of the rocket when the engine shut off. All right, so how high did it get? All right, so remember what we know here. We know velocity initially was 0. We know the time the rockets were firing was 11 seconds. The acceleration was 6. What else do we know? What else do we remember? Well, from the equation V equals AT plus V naught, that's where I got this 66 from, by the way. I just plugged in A was 6, T is 11. Initial velocity was 0, so I just did 6 times 11. So I know my final velocity is 66. Final, at least when the rocket shut off, right? My final velocity is 66. And I want to know my position. I know my initial position is the ground, so that's 0, initial x naught. What's my final position? Okay. For this equation, I'm going to need x equals 1/2 AT squared plus V naught T plus x naught. This part's kind of nice because the x naught is 0, so it goes away. V naught is 0, so it's going to also, this part's going to go away. So all I have left is 1/2 AT squared, so it's not too bad. So x equals 1/2. A was 6. T squared, T was 11 squared. So I get x, I'm going to do the math here. And calculator. I'm going to get divided by 2, 363 meters high. There we go, that's part B. Let's go to part C. Determine the maximum height the rocket reaches. Now, a lot of students want to say, isn't it just the answer from B? Isn't it 363? No, it is not. Let's go back to the graph and look and see why. The part in here is when the rocket is accelerating upwards. At this point right here, the rocket shut off. But the rocket doesn't instantly fall back to Earth, right? It takes a second. The rocket's got to slow down first, right? So imagine the rocket shooting up. Here's the rocket. And it's firing rockets. Firing rockets. Okay, rocket shut off. It's still got all its upward velocity, right? It's got a 66 meters a second of upwards velocity. Gravity doesn't work like it just instantaneously turns around, right? Think about a ball and you throw a ball up in the air. When you throw the ball up in the air, it still goes up, even though the only force on it is gravity. It's got to slow down first, and then it's going to fall back down. So rockets firing, speeding up. Okay, rocket shut off. It's still going to kind of drift upward, going to go up, and then eventually, okay, gravity takes hold of it, slows it down, stops it, and then it falls, right? So this whole area in here is also upward velocity. It's going up at that spot. How do you know? Well, look at the graph, right? Look at, if we trace it back over here, this spot right here, where does it go? That's a positive velocity. This here. That's a positive velocity. It's still going in the upward direction. It's just slowing down, but it's still going up, right? It's still going up. So we need to find out what the area of the graph is, this whole area, right? All that whole thing. Why? Because, well, actually there's a few ways we could do it. Area of the graph is one way to do it. The other way to do it is just use our kinematics equations. Why do we want to find the area of the graph? Because that area is displacement, right? Area under the curve of the velocity time graph is displacement, and that's positive displacement, positive going up away from the ground, right, up into the air. So it's one way to do it. Find the triangle and then solve. But I'm going to do it what I think is probably a little bit simpler and just use a formula, because we've already found how high it goes at this spot, right? We already know how high it is at the peak there, right? We know how high it is right here. It went 363 meters at this position. So all we really need to find out, okay, well, in all this time in here, how much more upwards does it get, right? How much higher does it go in that part of the graph, right? So I'm going to do the rest of the calculation. So we're going to go back to here and say, okay, so I'm at 363. Now, this is critical here. You got to consider, like, basically what I want to do in your head, you got to think, okay, I'm going to basically get rid of this whole part of the graph in here, I'm going to get rid of it. I'm going to ignore it. I've already calculated the height for that part of the graph. I don't care about it anymore. Ignore that graph and just focus on this section of the graph right here. Right? What happens in that section? Because I've already calculated the part. I don't need it anymore. I'm done with it. Let's just look at this part here. All right? So, all right. So what is my initial velocity then? What is, it's going to be 66, not 0, and so on. So let's go and write down our givens. I want you to do the guess method. Don't forget. It's going to help you. So what's my givens? Well, I know my initial velocity is 66 because that's how high I was when that's how fast I was going when the rocket shut off. Let's see, my initial position is my final position from part B, so my initial position is 363. My acceleration is now gravity, -10, because the gravity is taking hold of the rocket and now pulling it back down to Earth, slowing it down. And let's see, my final velocity will be 0, right? That's going to be how high when the rocket stops going upward, it's going to stop, right? As it goes up, stops, and then falls. And at the point where it stops, that's where it's highest it's going to get, right? It can't get any higher because it stopped going up. And what else do I know? I know determine the maximum height. I know T. Actually, I don't need T because we have a different equation. V squared equals oh, can I remember it from the top of my head? V squared equals 2a. I can't remember it. I gotta look it up. One moment. AP Physics 1 formula sheet. Huh? Oh my god, it's like recognizing. There it goes. Alright. Okay, so it's V squared. I got that part right. Equals 2a. I was pretty much right. 2a delta x plus v squared. Initial velocity squared. Alright, so I was on the right track. Alright, so this is a great equation. Like I said, you don't need t, right? So I'm looking for how much farther I went up, right? What's my final position, my x, right? How much higher did I get? Let's plug in our numbers. So v squared, well, final velocity is 0. 0 squared is 0. That's easy. 0 equals 2a is 10. Delta x is final minus initial. So final minus initial. Initial was 363. Plus v naught squared. Now v naught was 66. So I'll square that number. Alright, so I'm looking for x here. So I got 0 equals, this is -20 times x minus 363 plus 66 squared is a pretty big number. 4356. I'm going to go ahead and minus that over here real quick just to save room. So it's going to be minus 4356. So that number came from 66 squared, and I just subtracted it over to the side of the equation. Equals negative. I'm going to distribute the -20 now. The -20x plus. Because the -20 times the -363 is positive. That's 7260. What is it, right? And then I'm going to oh, it's an x, right? X. All right. And I'm going to subtract this over here. Oh wait, I got a square or something? No, I'm good. Okay. Now I'm going to subtract this over here. So it's going to be -4356 minus that guy. And that's going to be -4356 minus 7260 is -11,616 equals -20x. Divide by -20 both sides. And x is going to equal 580.8, which is the correct answer. There are lots of ways to do this problem. This is just one of them. You could have found what t was when vf equals 0, and then used, if you found what t was, you could then have used this equation, right? 1/2 at squared plus v naught t plus x naught. You could use that equation if you find t, and there's a lot of ways to do that. This is just one example of how to do it, right? Let's do part D and wrap the video up. Determine the amount of time the rocket is in the air. Okay. In the air, right? So the rocket's going to go up and then come back down and hit the ground. So we got to find out, all right, how long does that whole process take, right? First, we got to find out how long is the rocket going up for, okay? And in order to do that, we're going to use our kinematic equation. Let's go back to here real quick. That's this giant mess of a graph. Alright, so the equation that we've been using a lot, this guy right here, x equals 1/2 at squared plus v naught t plus x naught. Okay, that guy only works when acceleration is constant, right? But what the problem is that this part of the graph that I circled again, and this part of the graph here, I hope you can see this, is they have two different accelerations, right? So acceleration is changing. So we can't use that formula for the whole thing. We got to break it into chunks. So we got to chunk it like this. We're going to chunk this part of the graph, this part here into one chunk, this part here into a separate chunk, and then all the way back down. Now, actually, now that I think about it, we could chunk this part here all the way back down to the ground, right? Because it has the same acceleration. Once the rocket's shut off, the only acceleration is gravity pulling the rocket back down to the ground. So we could just have this two chunks. One chunk, this part in here, with a positive 6 acceleration, and the other part with a negative 10 acceleration going down. Let's do it that way, that'll be easier. Less math to do. Alright, so how long did it take for until the engine shut off? Well, we know that already, right? It's 11 seconds. The problem told us the rockets are firing for 11 seconds. That part was easy, that's done. So it's going to be 11 plus something, right? Now, okay, now how long did it take for the rocket to fall and hit the ground, right? How long did that process take? Well, we know at the height of the rocket, write down what we know, what are all of our givens. I'm going to erase a little bit here just to make room, okay? So you can go back and look at this again if you need to. I'm going to erase this part. I just need a little bit of room here. Alright, write down all of our givens. V naught. How fast are we going? 0, right? Remember, as the rocket goes up, slowing down, slowing down, slowing down, slowing down, and then for an instant, it actually stops, and then it falls back down, right? So initial velocity is actually 0. Time, we don't know what time is, so we want to know. Our initial position, that's x naught, is 580.8 meters off the ground. Our final position is going to be the ground, that's 0, right? And then what else do we know? Acceleration is negative 10, because gravity is pulling us down towards the Earth. Right? And it looks like this is a perfect setup for our trusty 1/2 at squared equation. And we just plug in our numbers. What's next? Alright, so this is 0 equals 1/2. A is negative 10. T we don't know, t squared. V naught is 0, so this whole thing goes away. So x naught is not 0 though, so we can't let that go away. So V naught times t is 0, but x naught was 580.8, so we got to put that in there. Okay, and then I'm just going to solve. I'm going to go ahead and subtract the 580.8 over to the other side of the equation. Negative 580.8 equals negative 5t squared. Half of 10 is 5. Divide by negative 5. So that's negative 580.8 divided by 5. And I'm going to square root that number, right? So this is negative 116. Sorry, not negative, positive, because negative divided by negative is positive. So positive 116.16 equals t squared. I got to square root both sides to get rid of that squared sign. So I square root that number. 116.6, and I get about 10.8. T equals 10.8 seconds. That's how long it takes to fall. That's not my answer though. Don't forget, I got to add that to the time it took to go up. It was 11 seconds on, or actually, let me think, 11 seconds. The rockets are flying for 11 seconds. Yeah, that's good. 11 seconds to here, to, this is like the messiest graph of all time. 11 seconds to hello? 11 seconds to, hello? Click it. 11 seconds to here, right? And then 10, 20 seconds all the way back down. Okay. So we're going to add those numbers up. So our total time then is going to be 21.8 seconds. We add these up. 21.8 seconds. And that's our answer. All right, cool. That was longer than I expected it to be, but if you made it all the way through, cool. You can skip around and you don't have to watch every little bit. Quiz Wednesday. Pictures tomorrow or something nice. Okie dokie. Bye-bye. Wait, hold on. Awkward. Okay. All right.